Let's talk about constructing a stack. But first, let's define what that even is. So a stack is an ordered collection of objects that follows this principle. Last in, first out. And probably the most common analogy for trying to explain what a stack is to look at the plate dispenser at a buffet. So here's the top of the table, and you see this plate right here, and we'll say it's plate number 4. But underneath this plate is plate number 3. Underneath that plate is plate number 2. And underneath that plate is plate number 1. So which one was put into the stack first? Because here's the stack. Well, 1. And then you added 2, which pushed 1 down. Then you added 3, that pushed 2 down. You added 4, that pushed 3 down. So the last one in is 4. But if you want to start getting plates from here, 4 is the first one back out. So if I take off 4, now I see 3 again. Take off 3, I see 2 again. Take off 2, I see 1 again. All right? If you saw some of my earlier videos in which we talked about the runtime stack, and actually in some of the videos I think I talked about a stack versus the stack. We talked about it in the context of what happens when a program calls functions. And I said that in many operating systems, a stack is what maintains the states. So if I have something like this, we had main, and I'm just simplifying some of the syntax here. We have a variable A with initial value of 1, and we call function F. And then we have function F. Inside that we have variable B, the value of 2. And maybe this calls function G. And so we close it up here, and then G works with variable C. Well, in terms of the stack, we need to maintain state, right? Because what's going to happen is in main, we create a variable called A. We call F. The flow of the logic comes down here to this function where we create B. Then we call G. The flow of the logic comes down to G where we create C. We do some stuff. We get to the bottom of the function, so we return where we came from, which is right here, back inside F. So something needs to remember where we came from, and also remember that at this point there was a variable called B with a value of 2. So we do some more stuff, get to the bottom of the function, go back to where we came from, which is right here. We need something that kept track of that address, as well as there was a variable called A with a value of 1, and so forth. So down here we have main, and it had A, and then we pushed, that's the term for adding here, F, and then we had B, and we had G, and with C, so forth. And then as we start to come back down, when we finish G, we pop this from the top of the stack. Now in reality, we don't erase this. They have something called a stack pointer, and the stack pointer was here before. It simply moves down, which says now if you need to overwrite this, so let's say inside function F, after the function called to G, we had a function called to H. Well, now H would be here, and the stack pointer would move back up, meaning if anything else needed to be added to the stack, it'd go right here. So things get pushed and popped with the stack, right? So that's one of the uses, but how do you actually construct one? Now I'm going to show you using a linked list, but you could also use an array, and some people do that depending on the application. So in terms of a linked list, we have something that looks like this. And we'll say these values of A, B, and C. Where do we do the push? Push here is equivalent to adding, and popping is equivalent to deleting nodes. So we push something onto the stack, which means adding a node either down here or down here, and we pop, which means deleting a node from here or here. Now from a theoretical perspective, it doesn't matter whether I add down here or add down here. If it's a stack, you just have to do the adds and removes from the same end. So I could add a node D down here. I could remove a node D if it was already here, that type of thing. But from a practical perspective, it does matter which end you use because of the amount of work it takes and what you know. Because what I have here is a singly linked list. So I only have arrows going in one direction. So if I wanted to add down here, which I could, right? I can create a new node. Here's temp, it knows the node. I set this to the null. But now I need to take node C and say that the next here has the address of temp. But I don't have necessarily something keeping track of this end. If all I have to get to anywhere in this linked list is to start with head and work my way down, well then every time I want to add a node, I have to start at head and navigate down till I find the null. Now I could do that and then say, well, where was I at the last time I did that, and then add it, but I'm still traversing this list. So really adds are easier down here because I already know where I'm at. And likewise, if I was talking about deleting, and I want to delete C, well, as I work my way down, I'd have to keep track of the previous node. So when I get here and say, oh, well, C is the last one, so now I need to free this up, and then also say, turn the next here into null. So adds and removes are really just easier at the head end of a singly linked list. All right? So what's the code for that? Well, I did that in another video where I introduced linked lists. I was basically using a stack. So we have head. So if I wanted to add the numbers, so if I want to push 1, push 2, push 3, that means this would have been the 1, this would have been the 2, this would have been 3 if I'm adding to the head end. So to add a new node, so if I want to push 4, then I'm going to have temp equals malloc. Get the size of the start node and all that stuff I'm simplifying. Temp, whatever the value is, we'll say it's x is equal to 4. Temp next is equal to head. That then calls us the new node. Temp currently points here, but I want temp next to point here, so this isn't really here, right? And now I need to move head. So head is equal to temp, and now it points here. That's pushing. So what about removing? We have head again. We'll say here was our 4 that we just added. 3, 2, 1. And when we're popping, we don't pass it a number because we're just saying get rid of the node that's at the top. And this is what we're calling the top. So when I just say pop, then we need to remove this. Now it's easy enough to do this. Free head. But what just happened? Well, where's this node at? I don't know anymore because the only way I knew about it was right here. I stored the address in the next component of this node to this. So I need to keep track of that because now I need to make head point to node 3. So instead what I'll do is this. I'll say temp equals head next. So temp points at 3. Then I'm going to free head. Free that. And now I'll say head equals temp. And so now it points over here. All right. So let's write the code to do that. So here I have part of what we need. Here's my structure. And then we're going to do this. We'll say head is equal to push head. And we'll give a variable I because I'm going to stick this in a loop. And let's make this, we'll make this 4, and we'll show we can do it independently outside the loop as well. And now we'll write the function. So I'm saying that it's returning something that's assigned to a struct node star, so that needs to be the return type. Struct node star. Whether or not I have a space there doesn't matter. And this is push, and it receives a struct node star. H, as well as some number n. We'll say int n. Now, could I call this head? Sure. If I call this head, it's still a different variable than this head. I'm just doing that so you don't get confused. But I could name the same thing because technically they're two totally different variables. It doesn't matter. So let's do what we said to add. Struct node star temp equals malloc. Struct node, or excuse me, size of struct node. Right, there's our space. We said we're going to store the data, which is an x, so temp x equals our n. Temp next is equal to h. So now I just attach this node to the head, and now I need to move what head points at. So since I'm doing it this way, I'm going to return temp because it gets reassigned to head down here. So let's see what happens. 3, 2, 1. And now if we say let's do that now. So I'm put this here and here. And let's change the way it prints actually to oops. 3, 2, 1, there's my 4. So what about now popping that from the list? Pop. We could do it different ways, just like I can do this different ways. I could pass in the address of head and then work with the pointer to that, but I think this is easier to read, so we'll do the same thing here. But this also has that option, passing the address or just returning the new value. Head equals, and let's see what this looks like. This we pop, and we don't pass it anything. Or actually, excuse me, I do need to pass it head because I do need to update there, so it does need to be struct node star h, but I'm not passing it a number to store. So for this, we said it would work like this. I'm going to have this temp variable. We're not allocating memory because of, we're not going to be storing anything. So what do we say we need to do? Well, we said temp will temporarily store head next. Then we can free head, or sorry, up here it's h. Yeah, so it's h here. And now this is where we would say head equals temp. But since I'm returning the temp value, the head equals temp part technically occurs here. Let's do a couple of these. So we had 4, so now we're back down to 3, and then we're down to 2. If I want to, I can do this. And we just added something. All right? So that's how you construct a stack in the simplest case. While we're here, let's go ahead and talk about something else though. So in a previous video, I talked about recursion and said that there were times when recursion was much simpler than some of the alternatives. So let's see how we can use recursion to print. So here's my print function right now. let's do this. Look at what I have here. And we'll make some changes to this actually slightly. So how does it work? Well, let's go back to our picture and say we pass in, so if head's currently pointing here, we pass this, we print it, and then we pass to the function again the address to the next node. So then we have another instance of the function in which we're pointing at this, so or have the address of it, print the number, pass the address of this to another call of the function. We get here, print 1, pass the null. So what's our stopping condition? If we ever get to the function and the address we were given is null, well then we return because we've ran out of nodes to print. So let's do that. So we said the stopping condition, if h is null, then we return. Otherwise, let's print the current value. So this was %d, and this will be h x, and then we call print recursive again, and we give it h next. So let's see what happens, and then we'll throw a print statement in here. Actually, (521) or 521. Right? So there's using recursion to print it. Now you may look at that and say, well, geez, didn't you already have a function that did that? I did. But let's see what happens if I do this. Swap these two lines. 125. What just happened? How can that possibly be? Well, let's think about what just happened in terms of the runtime stack. All right. So here's head. And it points at this node. So in my example here, we had 5 here. 2, 1. And so what happened? Well, we have the stack. And so we have this function that looks like this. So print recurse. It gets h. I'm simplifying here, so it gets something called h. And it says if h equal null, return. And then in this version, it says print recurse. And then here we have h next. And then here we had basically print x. So print f %d for the new line. And then we're at h x. And close it up. So the stack looks like this. So we first call it down here as main. And when we get here, what happens? I'm going to write over here, so this is the node. So this is node 5, the one that has the value of 5. And what happened? We said before you print 5, call function again. So here I have print recurse, and then it says print 5 when we get back. So we go over here. This is node 2. Print recurse, and when you get back, print 2. Over here, print recurse. When you get back, print 1. And then over here, it receives null. So it returns. And this was node 1. So we get to here, we return. Well, where we left off was here, so now we print the 1. Now we're at the bottom of the function, So we go back to where we came from. Well, we were called here, so we print 2. Then we're at the bottom of the function. So we return where we came from is here. We print 5. Then we return to main. So that's how we print 1, 2, 5. So since this is a singly linked list, how could I print this in the order 1, 2, 5 without doing this? I mean, there are ways, but I can't think of any that are easy. In my recursion video, I gave you a string that was something like this. And we did something logically equivalent to this, where each time I called the function, we printed a character. So we start with A, then we start with B, then we went to C. And we were using recursion, so we would print a character, and then we would pass the address to the next character to another instance of the function, and that's how we'd move along. And then we did the same trick of swapping the lines, and that's how we print in reverse. But because this is a null terminated array of characters, I could just use a loop to find where the end was at, or we can actually calculate it, but that still ultimately involves working your way down the list. But I could work my way down to the end, and then once I know where I'm at, then start working my way back. So I can do that here, but with a singly linked list, that's not an option. Now if this was a doubly linked list, where each node points in both directions, and if you had something like a tail here, then I could do this, something similar, by starting at tail and working my way back. But since we're working with a singly linked list, that's not really an option here. So I don't know an easy way of doing the equivalent of this without using recursion. And so I think this is a much more powerful example of the benefits of recursion than anything I've shown you up till now. Right? And then when we get to binary trees, I'll show you tree traversals that without recursion, I don't know how you really would do that either, short of maintaining your own stack. And why do that when the computer has one that you can use anyway? So anyway, that's how you construct a stack using a linked list and then do some navigation of the stack as well.